When we go to explain the MO theory behind the Allyl cation, the key thing to keep in mind is that the Allyl cation itself has 3 p orbitals in a row, all lined up with each other, and that's what creates the extended pi system that becomes both the double bond and the empty orbital. So what we have is a double bond that is made up by 2 p orbitals, creating a pi bond, and we also have an empty orbital on the nearby carbon that is, in this case, unfilled and is a cation. But what you actually have is all 3 orbitals aligned, so they're all physically aligned with each other. 2 of them happen to be filled, and 1 of them happens to be empty in this picture. 2 of them happen to be filled, and 1 of them happens to be empty in this picture. And then, of course, the reality is that this isn't the right way of thinking about it. The right way of thinking about it is as you have 3 different p orbitals and 2 electrons total with which to fill that system. And if you start thinking in those terms, then you're going to generate a different set of orbitals to work with. And fundamentally, that's what MO theory is about, being able to generate a picture that looks more like the actual reality than each individual Lewis structure that you might draw when you're thinking about resonance. So what you might not recognize here is that, ironically, even though it looks totally different from a Lewis structure perspective, the acetate is nearly identical from a MO theory perspective. The only thing that's different, really, is that here you have oxygen atoms involved in the actual structure itself. So this orange dot is a carbon nucleus, this orange dot is an oxygen nucleus, this orange dot is an oxygen nucleus as well, but you still have only 3 nuclei in a row. The atoms are different, but the nuclei are there, and now you have 3 different p orbitals, again, all aligned with each other. And in that sense, it's identical to the Allyl cation. Now, the other thing that's different is, in the case of the acetate, what we actually have is 4 electrons in this pi system. It's obvious you're looking at the double bond, that's 2 of them, but one of these lone pairs is also in this orbital. And so again, this picture results because you have 3 different p orbitals aligned with each other, and that creates 3 new MOs, 3 new molecular orbitals. And the only real difference is we're going to populate those MOs with 4 electrons in this picture, 2 electrons in this picture. And again, what we're going to end up generating is something that looks rather more like this, because this is the way the molecule actually looks, and we're generating this MO picture to get away from the relatively incorrect image that you might get if you're thinking in pure Lewis terms, and therefore resonance. The core idea for the MO theory approach is simply that you have these 3 p orbitals all aligned with each other, and therefore you can mix them to create 3 new molecular orbitals that are going to span the entire length of the molecule. And so you're going to have 3 different energy levels that result, and you can then generate what the shapes of these orbitals will look like. So what I've done over here is create this set of 3 orbitals, and the key thing to point out is that in this lowest energy orbital, there is no node between atoms. There is, of course, a node that runs along the internuclear axis. So in other words, the electrons are not allowed to be on the sigma framework of the molecule. The electrons are allowed to be above and below, and that's because we're looking at the pi system here. Whenever you mix together an extended series of p orbitals to create pi orbitals, the lowest energy orbital that you're always going to generate is going to be the one where they're all aligned with each other. So the phase of all 3 p orbitals is the same, and that will end up creating an extended pi orbital. So what I've done so far is just take all 3 carbon atoms and line them up with each other, and that's what I've done for all of these molecules, but there you are. And so if you take all 3 p orbitals and you put them together and allow them to overlap, what that creates is an area of electron density above and below the internuclear axis where the electron is allowed to be. And so what this orbital picture is telling you is an electron in this orbital can go anywhere in the molecule freely. It can be on this carbon, it can be on this carbon, it can be on this carbon, or anywhere in between. That's what this picture means. By contrast, the next energy level up, the next orbital up, when you mix 3 p orbitals together, you're going to create 3 molecular orbitals. The bottom one is going to be this one with the extended can go anywhere sense. But the next one up is going to have a node. And specifically, with only 3 orbitals and 3 atoms, that node is going to end up being right there on the central carbon. So said another way, the electron's allowed to be on this carbon or on this carbon, but it is not allowed to be on that carbon. Again, allowed to be on that carbon or that carbon, but not allowed to be there. And that's what this orbital is telling. Then, of course, the highest energy orbital for any of these extended p orbital pi systems is going to be strictly alternating, and that creates yet another node. The electron is allowed to be localized on any particular carbon, but is not allowed to be anywhere in between. So it could be here, here, or here, but not in between. Obviously, we have three different energy levels. The lowest energy one is the place where the electron can be anywhere between the nuclei and serve to bond. This will be a pi bonding orbital, and the lowest energy orbital for the system is always going to be one where the electron can move freely in the ground state, and that is going to be the pi bonding situation. Then here we have a non-bonding orbital. It's not bonding, but it's also not anti-bonding. The electron could be there or there, but it's not really anywhere else. And then the highest energy orbital is going to be one that we describe as an anti-bonding orbital. The electron is not allowed to be where it would do the most good to hold the molecule together. Instead, this is a relatively bad situation. Okay, so when we have allyl cations, specifically what we have is three p orbitals aligned with each other and two electrons to populate the system with. Therefore, what we end up doing is filling the lowest energy orbital and none of the others. We can then describe the orbital that is filled as the highest occupied molecular orbital. This is the orbital that has all of the electron density in it. And the next one up is going to be the lowest unoccupied molecular orbital. So the MO picture for allyl cation simply describes this. The electron density is going to be shared among all three carbon atoms. That's the dotted line there. And the place where the empty charge is, because this orbital is not full, is located on either of the two carbons on the ends, but not on the carbon in the middle. And that's because the empty orbitals are on the carbons at the ends and not on the carbon in the middle. The considerations for constructing the pi orbitals themselves are, of course, identical for both of the acetate and the allyl cation situations. And that is because it's simply a factor of mixing together three p orbitals. The only thing that's different now is that I have oxygen, carbon, oxygen as the nuclei, as the atoms around which these p orbitals are aligned. But you get the exact same scenario. You're going to mix together all three p orbitals in a row. So once again, the lowest energy orbital for the system is going to be shared evenly across all three atoms and in the spaces in between, and the electron is allowed to go freely anywhere it wants. Once again, this would be the pi bonding orbital, the one where all three p orbitals are aligned and of the same phase so that the electron can move freely. And then we have the next highest energy orbital, of course, once again having a node on the carbon atom, but the electrons are allowed to be on the oxygens. And this would be a non-bonding orbital once more.
In many ways, the most natural explanation for this non-bonding orbital is that it is the oxygen lone pairs. The electron is more or less allowed to be on either oxygen alone and not on the carbon in the middle. And again, the reason why it's non-bonding is essentially because it's an oxygen lone pair. It's not participating either in the bonding or in making the bonding worse.
And then, of course, the highest energy orbital here is going to be the pi star, the one where you have strictly alternating p orbitals, and therefore you have nodes existing between each of those p orbitals. The main thing that's different between the acetate case and the allyl cation case is that you now have 4 electrons to populate these 3 orbitals with. You have the double bond, the CO double bond, and you also have the O-, the lone pair on the oxygen. Therefore, we go ahead and fill the lowest energy orbital, and then we fill the non-bonding orbital as well. Therefore, if we start thinking in terms of frontier orbitals and naming which one is which, we would call this one the highest occupied molecular orbital, because of course this is the one that's filled, and then the pi star would be the lowest unoccupied molecular orbital. Much like the allyl cation case, the key thing to recognize here is that this picture now is very congruent with what we have drawn. There's double bonding character among both oxygen atoms and this carbon, and that's given by this lowest one, and there's a substantial amount of minus charge on either of the 2 oxygens, which is given by this orbital, and specifically there's no electron density, excess electron density on this carbon, because there's no electron density there in the MO picture. Once again, what we're trying to do by generating the MO picture is create this image, which is of course how the molecule looks, as opposed to relying on 2 separate images from the Lewis picture and trying mentally to average them together.